Welcome to lecture number 6 of fuzzy sets, logic and systems and applications. So, in this lecture we will be discussing fuzzy membership functions, and these membership functions are basically single dimensional membership functions. So, in the last lecture, while discussing the fuzzy membership functions, we had already seen these commonly employed membership functions, and you can see the names of these membership functions. So, out of these 10 membership functions, we have already covered 5 membership functions. So, remaining 5 membership functions, that is from left right membership function, we will cover in this lecture. So, let us begin with this membership function, that is left right membership function. Left right membership function is defined here by this function. So, you see here the left right membership function can simply be written as or defined as the LR of x semicolon C alpha beta is equal to FL of C minus x over alpha, and this is when we have x less than or equal to C, and FR of x minus C over beta, and this will be when x is greater than or equal to C. So, if we see here FL and FR, and these are just the functions. So, FL function and FR function, you see here FL function and then FR functions, and these FL FR functions are monotonically decreasing functions. So, this has to be noted, and these are defined on a strict interval here with FL, when we have FL of 0, and this will be equal to 1, and if we have FR also, so FR of 0 will also be equal to 1. So, we can also write like this as it is written. So, FL of 0 is equal to FR of 0 equal to 0. So, what does this mean here is that both the functions, when we have taken of 0, this will be equal to 1, and FL when x tending to infinite, means when x is approaching infinite, this FL will be equal to 1, and so not only FL, the FR also. So, both the FL and FR x tending to infinite is going to give you 0. Here these parameters C, alpha, beta, these 3 functions, basically these are the parameters which determine the shape of the left right membership function. So, C here defines the point C, this C defines the point where the value of membership function is 1, and alpha, this alpha controls the width of the left region for x less than or equal to C. Beta here, this beta in this left right function controls the width of the right region for x more than or equal to C. So, this way we define a left right membership function. So, let us take an example here to understand this better. So, if we write a code in MATLAB for implementing left right membership function with alpha is equal to 40, beta is equal to 10 and C is equal to 70. So, these 3 parameters if we substitute in this function and based on this function left right function, we will be able to plot left right membership function by using this MATLAB code. So, this MATLAB code you can simply write or you can copy and you can take this to MATLAB and you can run, and if you run this MATLAB code you will see that with these parameters you are going to get this shape. So, when you have alpha is equal to 40, beta is equal to 10, C is equal to 70, this kind of shape you are going to get. So, please note that the C 70 is the point here at which the membership function has its value 1. So, in other words we can say at C is equal to 70 the function has reached at the highest level and that is 1. And let me go back to the previous slide here, and we see here that as I have already spoken about FR here and FL. So, FR and FL both are the functions. So, in this case apart from these parameters alpha, beta and C, we also choose a suitable monotonically decreasing functions. So, here in this case FR and FL have been chosen as e raised to the power minus mod of u3. So, if we have substituted this function these parameters and we have taken the function included in this, we will be able to get the plot here as you see after getting these MATLAB code executed. So, let us take another example here to understand this better. Here in this example we have 3 cases for left right membership function plot. So, the first case here you see this first case in which we have alpha is equal to 30, beta is equal to 12 and C is equal to 50. So, if we take this value alpha is equal to 30, you see it means alpha is equal to 30, beta is equal to 12 and C is equal to 50. So, C is equal to 50 means this is the point that 50 is the point where this particular plot will have its highest value. So, if we see here the plot for these values, and let me make it clear here that here also we have used the same monotonically decreasing function. So, but we are only varying these the values of alpha, beta and C. So, these are the 3 cases. So, first case is where alpha is equal to 30, beta is equal to 12, C is equal to 50, and the second case we have alpha is equal to 30 and beta is equal to 12 and C is equal to 60. And the third case here is alpha is equal to 30, beta is equal to 12 and C is equal to 70. So, we can clearly see here that what we are varying here is the C only. So, in all the 3 cases we are changing only the value of C. It means we are shifting the point where we have the membership functions value 1. So, let me go back to the function definition. Here you see here it is clearly written that C defines the point where the value of membership function is 1. So, in this example, this C is changing. In one case we have 50, the other case we have 60, and then the third one we have 70. So, we can clearly see that for the first membership function, which is shown in blue. So, we see that here the membership value is 1, we see here, and the second case we have its membership value 1. So, this is the other membership function, the second membership function, the second case, and the third case here we have the membership value 1. So, this way we see that the C is the parameter which is changing in all the three cases. Rest two parameters are not changing at all. So, as we clearly know that the alpha is responsible for change in the left half of the region about C, and beta is responsible for the change of the shape the right half of the C. So, we can clearly see, once again I would like to tell you that these two values are same, alpha beta are same in all the three cases, only this C is changing. So, let us take another example here, where you see we have again three cases where we are only changing alpha. So, values are alpha are changing, you see here. See, in one case we have 60, the second case we have 50, and the third case we have 40, and other two parameters in all the cases are same, like beta C are same in all the three cases. So, if we see here C, since C the value of C remains same in all the three cases. So, let us see where this C is 70. So, you see 70 is this point, and around this, I mean this side is left side of this C, and this side is right side of this C. So, if we see here, as I already mentioned, that when we vary, when we change alpha, so we see clearly that left side of the curve is changing. So, this is responsible for the change in the shape of the left side, on the left side, and if we change in the other example, we see here that C remains same in all the three examples, and alpha remains same, see here 40. So, in all the three cases alpha C remains the same, only beta is changing. So, in one case we have beta as 5, and the second case we have beta 12, and the third case we have beta 20. So, beta is changing as 5, 12, 20. So, we see that C is here, C is the point, C is basically I can say it can be regarded as a center around which we have the left side. On the left side change beta is responsible, right side change the alpha is responsible. So, C here is at 70, and if we see very clearly, by changing the values of beta, we see that this side is the shape of curve is changing. The plot we can clearly see that the blue is for beta is equal to 5, and red is for beta is equal to 12, and yellow is for beta is equal to 20. So, this way we can control the shape of the left right membership function by changing alpha, beta and C suitably. Now, we can go to the other membership function, which is called pi shaped membership function. So, pi membership function, there are two types of pi membership functions. There are two functions basically. First function here is represented by pi 1. So, pi 1 function is having only two parameters. So, this can be expressed as pi 1 x semicolon a comma b is equal to 1 over 1 plus x minus a over b whole square. So, this pi membership function has only a and b, that means two parameters, and these two parameters actually control the shape of pi membership function. So, and then here we have another 4 variabled pi membership function. So, but this 4 variable pi membership function has 4 parameters. So, this pi membership function is represented by, is defined by pi 2 x semicolon L w comma L p comma L R p comma R w, and this will be equal to L w over L p plus L w minus x, and this is true for x less than L p, and then we have 1, this will be equal to 1 for all the values of x greater than or equal to L p, less than or equal to R p. And again we have one more case where this pi 2 x semicolon L w comma L p comma R p comma R w will be equal to R w over x minus R p plus R w for all the values of x greater than R p. So, this way we have two kinds of pi membership function. And here in the second case, so first case is represented by, first type of pi membership function is represented by pi 1, which is clearly mentioned here, and the other kind of pi other type of pi membership function here is represented by pi 2. So, pi 1 is only 2 variable membership function, and this function basically we can say this function has membership value at point A, membership value 0.5 at A minus B, which is mentioned over here, and A plus B respectively. So, unlike the function pi, function decreases towards 0 asymptotically as we move away from point A. So, this is here you can see represented by pi 1. Now, in the second case, which is represented by second type of pi membership function, which is represented by pi 2, this is characterized by 4 parameters L w, L p, R p, R w. Parameter L w and R w define the feet of the membership function, and L p, R p define its shoulders respectively. So, this is very interesting membership function which was used in the controller, fuzzy controller, which was very popular fuzzy controller used for the Sendai subway train control system. So, here we have the MATLAB code which you can use for plotting pi shaped membership function, and this has been given with an example, a case where we have L w, L p, R p, R w values given as 2, 5, 8, 10 respectively. So, we can clearly see here that this pi shaped membership function is the second type membership function, which requires 4 parameters. So, we see here the MATLAB code. So, if we write this code in the MATLAB and run this code in the MATLAB, we get this kind of plot. So, we see here the shape of this plot is pie type. So, we see here as I mentioned the LW, LP, RP, RW values, and I had already explained these parameters as this LW and RW define the feet. So, LW define the left feet, RW define the right feet, whereas LP define its left shoulder and RP defines its right shoulder. So, now let us understand this pie shaped membership function better, and for in this example we have taken 4 cases to better understand these parameters which are controlling the shape of the pie membership function. So, we have taken first case here where LW is equal to 0.5, LP is equal to 5, RP is equal to 7, RW is equal to 10. And as I already mentioned that LW is controlling left feet, LP is controlling left shoulder, RP is controlling right shoulder, RW is controlling right feet. So, we have taken 4 cases here. So, in first, second, third, fourth if we see the only LW is varying. So, this has done intentionally to make you understand that if we vary, if we change LW only, what is happening to the pie shaped membership function, and here in all the 3 cases only LW is changing, rest 3 parameters are remaining the same. So, here if we see, as I mentioned that the LW is controlling the left feet. So, if we see here the left feet is changing by varying the values of LW. Rest of the other values, all 3 values are the constant, the LP is constant, RP is the LP, RP, RW remains the same. So, that is why only feet is changing, and that is only left feet is changing, rest other things remain the same for this pie membership function. So, if we see here in all the 3 cases right feet remains the same, right feet is this. So, right feet remains the same, and then shoulder here the left shoulder remains the same, right shoulder remains the same. So, we clearly see that only by changing the LW only left feet is changing. So, this has to be noted here. And then similarly, if we take another example where we see that left feet remains the same in all the 4 cases, only LP is varied. So, we are changing the values of LP only, and we clearly see that left, since the left feet values are same in all the 4 cases. So, left feet remains the same. And what is interesting here to see that by changing LP, the values of LP in all 4 cases, you see the left shoulder is changing. This is clearly visible here that the shape of the left shoulder is changing. Similarly, if we take another example where the out of all the 4 parameters of pi shaped membership function, if we change only R p, that is right shoulder, and rest other parameters remain the same. If we see here, L w is not changing, in all the cases it remains at 2. So, that is why it is not changing, it remains the same in all the 4 cases. R w is 10 and this is also remains at the at 10. So, this is also not changing. So, it means that left feet is not changing, right feet is also not changing, and here if we look at the shoulders, like left shoulder, see left L p here in all the 4 cases remain the same and it remains at 4. So, this also remains the same in all the 4 cases. Whereas, since we are changing R p, so we see here the R p is changing, means the shoulder width is changing in all the 4 cases. So, first case we have R p is equal to 6. So, at 6 you see here the shoulder width is coming at 6, and then again if we are changing R p, which is here, is at 7, and then it is changing at 8 in the third case, and then again it is changing to 9 at in the fourth case. So, this way we understand as to how all these 4 parameters are changing the left feet, right feet, left shoulder, right shoulder of a pi shaped membership function. So, yes, so here we are changing the right feet, and if we change the right feet, here we see clearly that the feet is changing. So, in all the 4 cases in this example, only R w is changing, rest 3 parameters L w, L p, R p remains the same. So, here also we clearly see that the feet, the right feet is changing as per R w values. So, then let us discuss the open right membership function. So, in the open right membership function, we see that this kind of membership function is defined by open R x colon alpha beta. So, we clearly see that this function has only 2 parameters alpha and beta to characterize, and this is equal to 0 when x is less than alpha, and this is x minus alpha over beta minus alpha when x is greater than or equal to alpha and less than or equal to beta, and this is equal to 1 when x is greater than beta. So, when we try to plot the membership function, or when we try to draw a membership function based on this function, we will be going to get this kind of shape. So, this point on the x axis we will have as alpha, and this point here we will have as beta. And we can clearly see that this function is open in the right side. So, this is important to be noted. And similarly, for this also we have a MATLAB code for your help. So, you can clearly copy this MATLAB code, or you can rewrite this MATLAB code in the MATLAB, and you can run this MATLAB code with alpha is equal to 3 and beta is equal to 6. you will be getting this kind of shape. Similarly, since we saw here the open right membership function here, where open right membership function, because the right side of this membership function remains open. So, when we say right side of this membership function remains open, means limit x tending to infinite function, the open right function will always be equal to 1. So, when this function finally this function is going to attain the highest value, which is 1. So, likewise we have the open left membership function, and this membership function can be defined by open L x semicolon alpha beta, and this will be equal to 1 for all the values of x less than alpha, and this will be equal to beta minus x over beta minus alpha for all the values of x greater than or equal to alpha, less than or equal to beta, and this will be equal to 0 for all the values of x greater than beta. So, similarly, here also we have a MATLAB code that will help you to plot open left membership functions by substituting different values of alpha and beta. So, in this example we have chosen the value of alpha as 5 and value of beta as 7. So, by substituting these values of alpha and beta, we see here open left membership function, and we can clearly see that left side of this membership function is open. Open in the sense that we have the values, the final values, or we have the left side. If we take this value as alpha, this value as beta, this is alpha is equal to 5 and beta is equal to 7. So, left of 5, left of alpha is equal to 5, the membership function or the membership values, or I would say the membership function will have membership values equal to 1. Now, we come to another membership function, which is called S shaped membership function. So, S shaped membership function is defined by 2 parameters, and these parameters are A and B. So, this is defined by S shaped membership function is defined by f of x colon A comma B, and this will be equal to 0 when x is less than or equal to A, and this will be equal to 2 into x minus A over B minus A whole square for all the values of x greater than or equal to A and less than or equal to A plus B over 2, and this will be equal to 1 minus 2 into x minus b over b minus a whole square for all the values of x greater than or equal to a plus b by 2 and less than or equal to b. And this function again will be equal to 1 for all the values of x greater than or equal to b here. And let me also tell you that this parameter A defines the feet of the membership function and B defines its shoulder. So, like other membership functions, here also for S shaped membership function we have a MATLAB code ready for you, and if you would like to take this and execute in the MATLAB with A is equal to 4, B is equal to 8, we clearly see that this kind of membership function, the S shaped membership function, we are going to get. So, as I already mentioned that A, B, these two parameters are characterizing S shaped membership function. A controls the fit of the membership function and B controls the shoulder of the membership function. So, here we have few more cases. So, in this example we have two cases. The first case we have A is equal to 4, B is equal to 8, and the second case we have A is equal to 4 and B is equal to 9. So, we can clearly see that in this example the feet of the curve is not changing, feet of the curve is remaining at the 4. So, here A is equal to 4 we have taken, and you see the shoulder is changing here. The shoulder is the first shoulder is at B is equal to 8 and the second the shoulder for the second plot is at 9. So, by changing the suitable values of A and B, we can keep changing the feet and the shoulder. So, here as I mentioned that if we change the values of the feet, we suitably we can change the places of the feet. And here in these two cases we have B constant. So, B is not changing. So, that is why the shoulder remains at the same point. So, shoulder remains in both the cases same. So, this way the S shaped membership function can be plotted. And let me also tell you here, it is very important to mention that S shaped membership function, fuzzy membership function can also be used as the right open or left open type of membership function. So, this membership function, since the right side of this membership function remains at finally at 1 all the time. So, this qualifies to become the right open type of fuzzy membership function. So, with this I would like to stop here, and in the next lecture we will discuss the nomenclatures used in the fuzzy sets. Thank you very much.